my children, let us continue with voltaic cells. We started off with this in class today, and again, a voltaic cell is just one that will go through spontaneously a redox reaction. So you have to have some type of travel of electrons that will occur and make this voltaic cell. Now, I gave you an example today at how you can have direct contact between two of the species for a redox reaction to occur. When we have that direct contact, we don't want to think about that as being a voltaic cell because, again, we have defined a voltaic cell as a path where there's an external pathway for electrons to travel through some type of device. So that is going to be a voltaic cell. I'm utilizing all of this energy, which really we're thinking about that is just the work of making these electrons move. And that energy will then power up what I can see here as the voltmeter, so I can see an actual reading of current. So voltaic cell have to have an external pathway for the electrons to flow through. We talked about today how there are two different pieces, two really big components, I think, of a voltaic cell. There's the anode, and then there's the cathode. Now, the anode is always going to be that negatively charged terminal. And the anode is also where oxidation occurs. Oxidation we've already defined as being the loss of electrons. So since I'm losing electrons there, I'm building up all of these electrons so that they can travel through this external pathway over to the cathode side, which doesn't have this net charge, a net negative charge. So the cathode then we're going to deem with a positive charge. So anode will always be our negatively charged terminal. Cathode will always be our positively charged terminal. If the anode is where oxidation occurs, I'm losing those electrons. The electrons are going to have to move in some direction. So they're going to be directed from the anode toward the cathode. And that's just because electrons are going to be attracted to a positive charge. So here we come back to that Coulombic attraction. Because reduction is occurring then at the cathode, again, we'll call that positive. Now, for this voltaic cell to be electrically neutral, we said that we also need our final piece of this voltaic cell is going to have to be a salt bridge. Now, a salt bridge is just going to allow ions to migrate to keep the charge electrically neutral. I think I had you define that the purpose of a salt bridge today was to maintain that charge balance just because we have electrons moving from one half cell to the other half cell. And again, very common ones are NaCl or KCl. Those are the ones that we probably would prefer. Don't be surprised though if you see NaNO3 or KNO3. That's another one that maybe they like to use. But those are probably the ones that you'll see. Okay, if we didn't have a salt bridge, let's just kind of review about that again. If we didn't have a salt bridge, then we wouldn't be able to have any type of production of electricity. And that's just because the reaction then will happen so quickly that I'm not going to get any electron movement across this external pathway. So that voltmeter is actually going to read 0 volts. So I want to have production of electricity. So I need that salt bridge to keep everything electrically neutral, or to maintain, I guess what we would say in better chemistry jargon, electrical neutrality. So they could ask you, and I think I asked you this today, so we're just kind of reviewing for a couple minutes here first. I asked you today, how would ions migrate in a salt bridge to either of the half cells here? So we said, let's assume that this setup on this side at the anode is a piece of zinc metal in some zinc sulfate solution here. And then I have a piece of copper metal in a copper 2 sulfate solution over here on this side. Now, if at the anode I have oxidation occurring, then that means that zinc is being oxidized in that half cell. So that means if it's being oxidized, it's losing those electrons, which means that zinc is now becoming zinc 2+. So that's why I'm having That's why I'm seeing diminishing zinc metal here, because I'm entering more zinc 2 plus ions into solution. So I have more Zn2 plus in here. So to counterbalance that, what part of the salt bridge then would it be? In this case, I have NaNO3. Would it be the sodium ions, or would it be the nitrate ions that would enter then into this solution if I have more cations, more positive charge present? Well, it's going to be nitrate ions, because I need a negative charge to come over and balance then all of the zinc 2 plus ions that are coming into the solution because of the oxidation of that zinc metal. If I come over here to the cathode end, on the cathode end, I have all of my electrons coming over, so that way reduction is occurring at Cu. So I'm actually gaining electrons over here at this copper. So because I'm gaining electrons, I'm actually going to have the Cu2 plus come out of the solution and plate onto copper to become copper solid. So the blue color that we see will end up fading and diminishing because I'm losing copper ion and creating copper solid. So I'm going to have more sulfate ions in this, and again, sulfate anions in this solution than I will have cations. So I'll have more negative charge. So because of that, the positively charged particles of the salt bridge, so in this case sodium, are going to migrate their way over here into this solution toward the cathode side, just to keep and maintain that electrical neutrality. So hopefully that makes sense in terms of ion migration with the salt bridge, as well as the anode and the cathode, and I think the ideas behind them. So in the cell, electrons leave the anode and they will always flow through the wire to the cathode. So please highlight whatever you need to do to remember electron flow will always go from anode to cathode. And that should make logical sense. Electrons are never going to stay over here at a negative terminal. That's, I have likes repelling likes here. I want the electrons to have some type of Coulombic attraction, so those electrons are going to be attracted over here to the cathode side, that positive end. As the electrons reach the cathode, cations in the cathode are attracted now to the negative cathode. Electrons are taken by the cation, and a neutral metal is now deposited onto the cathode. So we've already explained that part. This is just bullet pointing, like giving bullet points to that. I tried to give this picture to you as well, because this is also another example of a voltaic cell. You don't necessarily see that U-shaped salt bridge. You will see that U-shaped salt bridge on your test. There's another type of salt bridge that we could do, and that's just using a porous barrier, which is what we could also say is a salt bridge, because I can have the cations start to migrate over here to help that electrical neutrality, and the anions that I'm getting because of the copper coming over here and plating on that copper metal are going to start to move over here to this side, since I'm making too much Zn2 plus on that anode side. So I could have a porous barrier as well. That is very, very rare. We'll probably have more of the U-tube shaped salt bridge. We have a type of notation for writing electrochemical cells as well. So let me show you what that notation is. And it's actually a lot nicer than necessarily having to write out the reaction. Let me first just find my Promethean board pen. Okay, so for electrochemical notation, again, because always electrons are moving from the anode to the cathode. So we've been focusing on this reaction here. I have zinc metal and I have copper 2 plus ions, and then that's going to react to form copper metal and then zinc 2 plus ions. So if I think about what's being oxidized, what's being reduced, then zinc is what's being oxidized and copper is what's being reduced. So if I asked you what would be at the anode, you would tell me it would be zinc, because remember, N-ox would be, anode is where oxidation occurs, and red cat, so reduction of copper has to be then at the cathode. So electrochemical notation, we can write the anode, so what's happening at the anode, and then these two double lines here represent your salt bridge. So I have what's happening with the anode, or that oxidation step. salt bridge, and then what's happening at my cathode. If I have this reaction that I'm starting off with, this would be my electrochemical notation for this particular reaction. So I have zinc is being oxidized to form zinc 2+. Again, 2 lines to represent salt bridge. So you'll note that I have one single line separating. This is what I'm starting off with originally. It's going to go through oxidation to make Zn2+ ions. Okay? So these are just separating. This is what I'm starting with. This is what I'll end up forming. Salt bridge, Cu2+. This is what I'm starting off with. And I'm going to end up plating copper solid, and that's because I'm going through my half-cell reduction step. So this would just be notation. They may give you this instead of giving you this. I may give you this and ask you to write a reaction for this. But these two things are really, truly, in essence, the same thing. They're just a different way to show them using different types of notation. Okay, so let's look at this question. It says, the oxidation reduction reaction that you have here is spontaneous, meaning it's just going to occur on its own. It says a solution containing K2Cr2O7, potassium dichromate, and H2SO4 is poured into one beaker, and a solution of Ki, potassium iodide, is poured into another. A salt bridge is used to join the beakers, so I'm creating some type of a voltaic cell. A metallic conductor that will not react with either solution, like platinum foil, is suspended in each solution, and those two conductors are then connected to wires, which is connected to a voltmeter, so I have my external pathway that can see any type of production of electricity. The resultant voltaic cell generates an electric current, so we know that this reaction is happening. Indicate the reaction occurring at the anode. Indicate the reaction occurring at the cathode. Indicate the direction of electron migration, the direction of ion migration, and the signs of the electrodes. That's a lot of stuff to do, but this is a really easy question. So just because this is a super long thing, it's not hard, I promise. Indicate the reaction occurring at the anode. So first thing I want to do, if I want to know what's happening at the anode or the cathode, I need to figure out what's being oxidized and what's being reduced first. And how do I do that? I do that first by determining all of the oxidation states that are up here in my overall reaction. So, just for peace of mind's sake, product side chromium has a +3. If I look over here on the reactant side, chromium is in my dichromate anion. So chromium on the reactant side is going to have a +6 charge. So I'm going from a +6 to a +3. So since I'm becoming less positive, it must be going through reduction. So chromium must be going through reduction. If I look at oxygens, a -2 here, a -2 here. So oxygen, nothing's happening with it. Hydrogen's a +1 here, hydrogen's a +1 there, nothing's happening with it. Iodine is a -1 here, but is now a 0 here. It's becoming more positive. So since it's becoming more positive, it must be losing electrons, meaning that it must be going through oxidation. So chromium is being reduced. Reduction happens at the cathode. Oxidation happens at the anode. So that means for the first part of my question, indicate the reaction occurring at the anode. If I know that iodine is being oxidized, then that means that iodine has to be at the anode. Specifically, though, they gave us a compound for it. It says, where is it? And a solution of Ki is poured into another beaker. So I would say Ki is your anode. Then that means K2CrO2 and H2SO4 is going to be where your cathode is. And that makes sense because Cr is what's being reduced. The next part of that question, so we answered both of those questions there. The direction of electron migration. Electrons always move from anode to cathode. That's all you have to say. Question answered. The direction of ion migration. If I have a salt bridge, then what will be moving toward Ki? What would be moving toward the Cr2O7? So I would say that cations would be moving toward the cathode. Because remember, let's see if we can go back here. So cations are going to be moving toward the cathode, and that's because I had Cu2 plus, if we go back to the reaction that we were looking at before. I have Cu2 plus in this beaker, and then I'm gaining a lot of electrons, so now that Cu2 plus is going to be reduced. It's going to gain an electron and plate onto copper, meaning I'm going to start getting a lot more SO42 minus in this beaker. So I have a lot more anions now. I need the cations to come in here to balance out that electrical neutrality. So for cathode, cations will move to the cathode, anions will move then toward the anode. So hopefully that makes sense. So we have that, and then the signs of the electrodes. Anode's always going to be negative, cathode's always going to be positive, so we answered that question too. Next one, the two half reactions in a voltaic cell are given to you as follows. It says indicate which reaction occurs at the anode and which at the cathode. So I could do this in two ways. Really easy for me right now to say this half cell reaction has the electron count here on the product side. If I'm creating or losing electrons, then zinc has to be the oxidation step, which means that oxidation or zinc has to be at the anode. So this one then has to be the reduction step. So if I have 6 electrons that are here on the reactant side, it means they're gaining electrons. I know that that's what happens in reduction. And then you'd be able to see that it would be chlorine that's specifically what's going to be reduced. And then it says which electrode then will be positive. Remember, the positive electron, or the positive electrode is the one that's going to be at the cathode. And we said that the cathode is reduction, so that's going to have to be here, the ClO3 minus plus the 6 hydrogen, that particular setup there. Okay, let's talk about electromotive force, or what we would also call as EMF. So let's be zen for a second. Let's get into a meditative state, and let's give an analogy. And we think about a waterfall. So nice. I hope none of you have to pee right now. Water spontaneously flows only in one direction. Specifically, when we're really thinking about a waterfall, you're never going to have water moving from a lower potential energy up to a higher potential energy. Instead, things want to move from a high potential energy to a low potential energy. So just like the flow of water for a waterfall is spontaneous, I want you to think about electrons as flowing spontaneously only in one direction. And again, we already said that's from anode to cathode. If the anode is negative, electrons don't want to stay next to a negative terminal because it's creating a lot of repulsion. So they're going to want to move spontaneously to a positive terminal, the cathode. So let's think about it then in a different way. Instead of saying that they're moving from negative to positive, we're going to say it's moving from a higher potential energy to a lower potential energy, okay? We have then defined this potential energy difference between the anode and the cathode as the electromotive force, or what we'll also call EMF. You may call it electromotive force. AP Chemistry likes to call it something else. We like to call it cell potential, which is also designated as the voltage of a cell. The cell potential is measured in volts. Makes sense. If we call it voltage, it should be measured in volts. And 1 volt is also equal to 1 joule per that capital C. Do you remember what that is? Coulombs. So coulomb, think about charge. And then you're also think about too the charge of an electron, and you would be able to find that on your constants page for your AP chemistry test, but the charge of an electron is 1.60 times 10 to the negative 19th coulombs. So when they're talking about coulombs in charge, it's not talking about like -1, -2. They actually want the charge of that electron then, okay? So electromotive force, just thinking about how electrons are moving from anode to cathode, and it's the potential difference. So thinking about where they are at that highest potential energy moving toward that lowest potential energy. Think about your waterfall. It's finding a number and a calculation for that. Today in class, I handed you a standard reductions potential reference page. This was used all up until last year. They now have said, I do not want AP Chemistry students to have to look up during their test a standard reduction potentials chart. So all of these numbers that you have will be given to you and will be embedded within a question, which is really nice for you. It really sucks for the people that had to take it all previous years, but I think that it's a really good time saver. And for us though, I have not embedded them in your questions, which is why you have that page. So if I give you a question and you need some type of voltage, or you need what we would call E-cell, which is just the cell potential, then you will find it on that standard reduction potentials page. I'm going to post one, so I gave you one in class. I'm going to post one that's here from your book, because a couple of the problems that we'll talk about here, you'll need the one specifically from your book. Again, they'll be embedded, so that's a really nice thing. Let's talk though really quickly about what this standard reduction potential means. You'll see at the very top of that reduction half reaction, all of these are based on reduction half reactions. So if I'm thinking about what would be the best element that would go through reduction, and reduction means gaining electrons. So what element more than any other element that I know of really wants electrons? Fluorine does. So fluorine is a very good at being reduced. There's another way I could say that. I could say that fluorine is the best oxidizing agent. Okay? That means then that something like an alkali metal is going to have to be the worst at being reduced, because it really wants to give away its electrons. So I should see alkali metals down here at the bottom, and I do. I have sodium down here, and I also have lithium down here. So they're the worst at being reduced, or I could actually spin that and say they're the best at being oxidized, right? Which means that they're the best reducing agents. So I could say these in a couple different ways, and we'll have to just know that jargon. You'll see that some of these have positive values, some of these have negative values. If they have positive values, if your overall cell potential for an overall electrochemistry reaction is positive, it means it is a spontaneous process. It means it will occur on its own. If you have the overall cell potential for a voltaic cell as being negative, it means that it will not happen spontaneously. It is a non-spontaneous process. We will relate, because we've only really talked about spontaneous and non-spontaneous processes with delta G. Guess what? I know you're so excited. Delta G and E are so related to each other. And then you thought you were done with equilibrium, but that's related too. I'm so excited, so we'll get there. Okay, how did we find out the standards? Let's talk about that. So all of these are based on a standard. So they're all happening at 25 degrees Celsius, aka 298 Kelvin. We found this standard by creating a voltaic cell with one of those particular elements that we're looking at, what we're trying to find the measurement for. And then we also created what we would call the standard hydrogen electrode. This standard hydrogen electrode is actually pretty cool. We call it She. It's a She electrode, or just a She electrode, which actually is kind of redundant since the E means electrode. So a She consists of a platinum wire, and that platinum wire is connected to a piece of platinum foil. So I don't know if you can really see that there. It's probably really hard. But you have this platinum wire, and it's connected to just some piece of platinum foil. And then we're going to cover that, and we end up connecting it where we can have a stream of hydrogen gas, as well as just 1 molar of hydrogen ion somehow within that electrode. And we have found that that will give us a voltage of 0. So we have created and defined that this is just going to have a voltage of 0. So then whatever voltage I see that's coming on the voltmeter is totally coming from the other half cell. So that's how we've created these standards for these cell potentials of each individual reaction that we'll deal with. It's very commonly used. We have, if you look in the back of your book, some appendix, I don't know, E, F, whatever. One of your appendices has all of the standard potentials in there. So again, use the paper that I've given you in class today, or use the paper that's on your blog. You may see either one of them. Because I want to know what happens in a system. So I have an oxidation step, I have a reduction step. Because I have those, I want to find the cell potential for that entire system. Well, how do I do that? We're going to do that by saying the cell potential for that overall voltaic cell is going to be equal to the cell potential that happens at the cathode minus the cell potential that happens at the anode. How will I know these two? On your AP test, they'll be embedded in the questions. So it will tell you cell potential for one reaction, and then they'll give you another half reaction and tell you the cell potential. And then you'll probably have to figure out what's at the cathode, what's at the anode, and then find out the overall cell potential. Okay? It is an intensive property, and that intensive property just means that if I change the stoichiometric coefficient, or if I change the stoichiometric amount of what I have in a half reaction, it is not going to affect the value of that standard reduction potential at all. So remember to think about this as being as an intensive property. Okay, let's look at an example. So let's say that I have zinc metal in a zinc nitrate solution, and I also have then my She over here. Salt bridge is going to be Na plus and NO3 minus. Zinc is being oxidized, it's over here at the anode, and the She then is going to have to be acting as the reduction half step if this is what's being oxidized. So we see on the voltmeter that this is reading a 0.76 volts. So we have over here as our standard for zinc a negative 0.76 volts. We know that the reduction over here for the She is just 0. So pretend like this math doesn't exist down here, because I actually did it for another one. I want to follow and use this reaction though here, or my equation, that I'm going to take whatever that cell potential of the cathode is minus the cell potential of the anode. So the anode is where oxidation occurs, cathode is where reduction occurs. So instead of this 0.34, pretend like that's 0. So cross that out, la la la, I don't like it. That's a 0 minus a negative 0.76 volts. Okay, if I do that, I'm going to get this to be a positive 0.76 volts. A positive cell potential means that this is a spontaneous process. It means that it's very easy for zinc to go through some type of oxidation and then have electrons travel spontaneously over here then to that She electrode. Okay, let's look at another example. This is for the zinc copper 2 plus voltaic cell shown in the figure right here. So literally the one that we've been looking at this whole time. It says we have the reaction here to the left. So they give us the reaction. They also give you the cell potential. So they're telling you that on the voltmeter, this whole reaction is giving me 1.10 volts. Given that the standard reduction potential for zinc 2 plus to zinc is negative 0.76 volts, I want us to calculate the reduction from copper 2 plus to copper. So I know I'm just going to follow again. My cell potential for the overall system is equal to the cell potential of the cathode minus the cell potential of the anode. I know the overall cell potential is 1.10 volts. I'm going to set that equal then to zinc. If zinc is at the anode, that means that's what's being oxidized. I don't know what's happening then at the cathode. So I would say 1.10 volts equals X minus a negative 0.76. So really I'm just subtracting 0.76 from 1.10, and then I'm going to get an answer of 0.34 volts. So the standard reduction potential for copper 2 plus to Cu should be 0.34, and it should be positive volts, okay? So hopefully that makes sense. It's really, really easy to use. Again, all of these numbers will be embedded for you in your question, just like I had them here. You just have to know that formula. It's always going to be cathode minus anode. Okay. Same thing that you're doing here. I'm going to skip it because you know how to add and subtract. Okay, next question. This says, using your table 20.1 from your book, and actually, I think you're going to have to use the table that I gave as an attachment on your blog, just because there are some of these that are not on your standard reduction potential table that I gave you today in class. So this says, using that table, calculate the voltaic cell, which is based on the reaction. So if you would look up if you would look on your standard reduction potentials page, you could find the cell potentials for each half reaction, subtract them from one another, get the overall cell. It's really, really, really not hard. So again, I'm not going to go over these either because all you're doing is subtracting. You're looking in a table and subtracting. And then I even eliminated that for you on the AP test. Look how amazing that is. You don't even have to look it up anymore. Okay, let's look at this one. A voltaic cell is based on two standard half reactions. I have cadmium 2 plus and I have tin 2 plus. It says use the appendix E or whatever that we have. I'm actually going to give you the cell potentials for those. So using your cell potentials that I'm about to give you, it says which half reaction occurs at the cathode, which half reaction occurs at the anode, and tell me what the standard cell potential will be. So if this were an AP question, they would tell you, I give you this, and then they'd say E reduction equals a negative 0.40 volts. They give you that whole reaction that they gave you on your problem, and then they'd say E reduction is an E naught reduction is equal to a 0.14 volts. How do I know what would be at the cathode and what would be at the anode? The more positive your E means, the better it is at being reduced. Because all of that, remember, if we're looking at that standard reduction potential page, fluorine is at the very top. It is so good at being reduced, it wants to gain electrons. So I'm looking then for a positive number to have reduction, and reduction happens at the cathode. So whichever one of those numbers is more positive, that's where my cathode is. Tin is a negative 0.14, cadmium's a negative 0.40, so that means tin has to be the cathode. It's more positive than the 0.40. So cadmium's my anode, tin is my cathode. If I wanted to find then the overall cell potential, I'm going to take the cathode cell potential minus the anode cell potential, which would then give me a positive 0.26 volts. If that's true, if they're asking me to figure this out and this to happen spontaneously, my overall cell potential better be positive. And this is just showing me then that I chose the right cathode and I chose the right anode because I'm getting a positive cell potential here, meaning it's happening spontaneously. Okay, let's also talk about oxidizing agents versus reducing agents. So the strongest oxidizers have the most positive reduction potentials. Strongest reducers are going to have the most negative reduction potentials. Okay, so we've really already talked about that in terms of thinking about it with your standard reduction potentials page. Again, fluorine, like we saw, that was on the top. Because fluorine is on the top, it has the most positive value for that cell potential, and that's just because it's the most easily reduced species, which makes it then the strongest oxidizer. So the strongest oxidizing agents, when I say strongest oxidizer, I'm meaning strongest oxidizing agent, has the most positive reduction potential, because oxidizing agents is the same as reduction. The strongest reducing agents have the most negative reduction potentials. And again, That's because they really want to lose their electrons, versus in reduction, we're really trying to gain those electrons. I have seen your standard reduction potential page flipped. So instead of being a standard reduction page, we're really thinking about it in terms of oxidation instead. On your test, we always will think about it as reduction potentials. So we'll always think about it as fluorine being on top and lithium then being on the bottom. So always think about it in terms of reduction. The greater the gap, the greater the difference between your cathode and your anode, and the greater the difference between those cell potentials, those individual half cells, the greater the voltage that you're going to have for the cell. So think about the waterfall analogy again. The more height that I have from that higher potential energy where the water is about to flow off of that cliff, the more height I have, then really the more potential energy that I'm going to have, because there's a greater gap in between the cliff and the ground. Using your either table 20.1 or using, or also using your standard reductions potential page that I gave you in class, this says rank the following ions in order of increasing strength as oxidizing agents. So I think I have this table on here. Let's go back to it. Let's see if we can't find it. Okay, let's look here. So this is your table 20.1. They asked me about NO3. So NO3 is right here. They asked me about Ag, which is right underneath NO3. And then they asked me about Cr2O7, which is above both of them. And they said they want us to rank the following ions in order of increasing strength as oxidizing agents. Okay? Standard reduction potential tells me if something is good at being reduced, it's going to be a really good oxidizing agent. So the more positive this value is over here, the better oxidizing agent it will be. So if I have to go from order of from decreasing to increasing, or from smallest to largest, I'm going to say silver will be not so great at oxidizing as being an oxidizing agent. Nitrate ion will be next, and the dichromate ion will be the best oxidizing agent. So I would go Ag, NO3 minus, Cr2O7 2 minus. Okay. The next question says rank the following species from the strongest to the weakest reducing agent. I'm going to let you try that one, and then we will check together and talk about it on Monday. Free energy and redox reactions. Oh my gosh, we are so close to talking about delta G and E, and it is so exciting. A positive value of E indicates that a spontaneous process occurs. Guess what? We already talked about it. Negative value of E indicates that a non-spontaneous process occurs. So this is the exact same thing. Reduction is where the cathode is where reduction is happening. Anode is where the oxidation reaction is happening. So same formula, same idea of what we've been doing. These are just asking you whether these reactions would be spontaneous or whether they would be non-spontaneous. And you would know that because you'd have to look up. So I would have to think about what's happening with each of these half cells. So let me say, for example, that copper, so when copper is oxidized, it has a cell potential of a positive 0.34. Hydrogen, I have this H plus to H2, that's going to be that She electrode, and that gives me a standard potential of 0. If copper is being oxidized here, that's the anode. Hydrogen is being reduced, that's the cathode. I would do 0 minus 0.34. So that would give me a negative 0.34. Because that's negative, it means it's a non-spontaneous process. So A is probably something that is not likely to occur by itself. Well, it is something that's not likely to occur by itself. It's a non-spontaneous process. It's something that we wouldn't see very readily happening just in nature. We can do the same thing for B and do the same thing for these, but all you're doing is looking up, which you don't have to look up on your AP test, but you'll have to look up here. They'll be embedded in the questions. They'll give you the cell potentials. You determine if they're spontaneous or not by taking cathode minus anode. Get it, if the number is positive, it's spontaneous. number is negative, it's non-spontaneous. Now that's opposite to what we know as delta G, because remember that delta G tells me if delta G is negative, that means the process is spontaneous, and if delta G is positive, that means the process is non-spontaneous. So do not get those two mixed up. So let's talk about delta G, because it's fabulous to build bridges and relationships here. Delta G for a redox reaction can be found by using this equation here. So delta G is going to be equal to a negative N. What on earth is N? N is the number of moles of electrons that are going to be transferred. So how do I know that? How do I know how many electrons are transferred? You have to write out each of the half reactions and figure out how many electrons I'm either gaining or losing, and then that's the number I'm going to write in there. It's going to be unitless. Okay, so think about that as just kind of being this unitless entity right now. F is a constant. We call that Faraday's constant. Faraday's constant is 96,485 coulombs per mole. You'll probably never use this one. You're probably going to be using this one. The 96,485 joules per volt mole. Okay, so same number, just using it in a different unit. Under standard conditions, so this would be under non-standard conditions, we usually do these things with standard conditions. So if we're thinking about it 25 degrees Celsius, then my standard here for delta G is just going to be equal to the same thing, but now it's at a standard cell potential. So how do J and K and E all relate to one another? And actually, let's go back really quick. Sorry, I lied. E. If E is positive, that means that that voltaic cell is trying to happen spontaneously. That negative sign then tells me that delta G will be negative, which means that that should be a spontaneous process. If E is negative, meaning a non-spontaneous process, that will give me a positive delta G, which then tells me again that the process is non-spontaneous. Okay, so how do G and K and E relate? Let us look. I know that delta G is equal to a negative NFE. So that is how G and E relate to one another. How do I get K in there? How do I show a relationship at least between E and K? I know a relationship from the previous chapter between G and K, because G is equal to, standard G, is equal to a negative RT times the natural log of K. If I know this piece and I know this piece, I just rearranged this equation, but for the cell potential, that standard cell potential. I just said that G was equal to this, so let me just plug all of this in here. So I just plug delta G, standard delta G in here, over negative NF. Negatives are gone. I have RT over NF times the natural log of K. So standard cell potential is equal to RT over NF times the natural log of K. So these three big pieces are ones that you'll have to remember. If you had an FRQ question, that short answer question, they're probably going to go here, or they're going to go to our very last equation that we still have to do called the Nernst equation. And then it wouldn't be a short answer question if they didn't have you doing one of these things. Okay, so hopefully you have those down. I want to utilize these equations now. Okay, so let's just do A first. Let's just focus on A. Use the standard reduction potentials in table 20.1 to calculate the standard free energy change delta G and the equilibrium constant K at 298 Kelvin for the reaction. So I know this is at standard conditions because I'm at that 298 Kelvin. The reaction that they gave me was solid silver is reacting with oxygen gas and hydrogen ion to create, or to produce, silver ion and then water. For time's sake, I went ahead and worked this out. So follow me here, okay? Don't freak out by all of this yet, just stay with me. So I had to write out first what's the oxidation step, what's the reduction step. Now, in this problem, if this were an FRQ or multiple choice, they give you these. These are going to be given to you. You don't have to look them up. I have oxygen reacting with hydrogen ion, that was a minus, hydrogen ion to make water. So I'm going from a charge of 0 for oxygen to a charge of -2. Meaning then that this has to be my reduction half reaction. To balance electrically, I added 4 electrons then to my reduction half reaction cell here. I next did the same thing for oxidation. I went from 4 Ag to 4 Ag+. Since oxidation is where we're losing electrons, I added on the product side then losing that 4 electrons. So they gave me then this, or I'm giving you this, that for this oxidation reaction, cell potential is a positive 0.80 volts. For the reduction half reaction, I get a positive 1.23 volts. So first they ask me, what's delta G? And then they ask me, what's K? I'm going to go to that reaction. Delta G is equal to a negative NFE. I don't know E, so I need to figure out what E would be. They've given me these, so I have to find the overall cell potential, cathode minus anode, or reduction minus oxidation. So I'm going to do 1.23 minus 0.8, and I get a positive 0.43 volts. So there's E. Now I have enough information to find delta G. Delta G then is going to equal a negative N, that's the number of moles of electrons. I had 4 electrons, 4 electrons. So in this overall reaction, there's a transfer of 4, so that's why I have that 4 there. So you have to balance these half reactions electrically to know what N will be. F is a constant. That's on your constants page, 96,485 joules per volt mole. Then I have my E value, which is a 0.43 volts. If I do that math, I get G to be a negative 170 kilojoules per mole. That's not the last thing they asked me to do, though. They also asked me to find K. So to find K, since my gas constant R, because K and G are related, by saying delta G, the standard delta G, is equal to a negative RT natural log K. I know R, I know T, I know G because I just found it, but R is in joules. I have to convert this then back to joules.